We're going to start off today's lecture by reviewing some of the rules, some of the naming rules, some of the other things that tend to be difficult for students at this time. I know that we've done this before, but it's been my experience that this part of the course needs to be repeated over and over and over again in order to ensure that we learn from our mistakes. So let's go through these rules again. First of all, we have to remember that certain elements in certain families regularly have the same oxidation numbers. This rule is called the specific oxidation number rule. And the reason I mention this is that I noticed that in some of the homework and the original quiz, the previous quizzes, there was some not detecting this rule, that this rule exists. Now, this does not mean that there are never exceptions, but many times these exceptions, you have to remember that exceptions are exceptions because they don't happen very often. The first of these rules is that group 1A, these are the column of elements on the left side of the periodic table, the alkali metals, almost always have an oxidation number when binding with other elements of +1. That is rarely not true. The second is that group 2A elements, those are the second column or second group of elements on the left side of the periodic table. The group 1A elements are lithium, sodium, potassium, etc. The group 2A elements are magnesium, calcium, etc. They're called alkaline earth metals, and they are almost always have an oxidation number of +2. Hydrogen has an oxidation state of +1 when it is bonded with another nonmetal. Let me say that again. Hydrogen is a +1 when it's bonded with another nonmetal, that would be such as chlorine or fluorine or bromine or oxygen, etc. But then has a oxidation number of -1 when it's bonded with metals such as sodium, potassium, etc. Oxygen is almost always -2, except when bonded with the highly electronegative fluorine. And group 7A, the halogens, are -1. Now this is the important part. They're -1 when bonded with metals. When bonded with metals. Let me say that one more time. When bonded with metals. The times when halogens have an oxidation state or an oxidation number other than -1 is when they are bonded with nonmetals like oxygen, like fluorine, like sulfur, etc. So just remember that these rules, try to get these rules in your head. Try to keep working with this until it becomes second nature to you. So let's practice this. And this was a question that was in some of your on your quiz and in some of your homework. So let's take a look at this. Give the oxidation number for the underlying element in each compound or ion. Okay. We have barium and then a carbon and oxygen combined together. Now remember that I said the 2A element, that's barium, has a +2. And remember that I said oxygen was almost always -2. And from the lectures previous, you'll remember that a compound like this, this is barium oxalate, by the way, a compound like this has a overall oxidation state of 0. It's a compound. And so the sum of all the oxidation numbers has to equal 0. Well, let's take a look at this. We see that if barium is a +2 and oxygen here is a -2, we have +2 plus 4 times a -2 plus 2 times something has to equal 0. So that's plus 2 minus 8, so that's 6. If we pull that 6 over on minus 6, we pull that 6 over here, it's going to be 6 is equal to 2x. So the x in this case has to be plus 3. So carbon in this case is a plus 3. Now you see that it's a 4A element, and you would think that it would be plus 4. Sometimes it's minus 2. But in this particular case, it is a plus 3. Now let's take a look at this next one. Now remember, the sum of oxidation numbers of a polyatomic ion has to equal the charge of that ion. So that means that here we have hydrogen, which is a plus 1. It's binding with a nonmetal, so it's plus 1. This is a nonmetal, this is a nonmetal, so it's a plus 1. We have sulfur here, which is what we want to know, so we'll call that X. And oxygen again, which is a minus 2. Now we have 4 oxygens, so it's 4 minus 2. So the sum of all 3 of these has to equal a minus 2, because that's the charge on the ion here. So we have plus 1 minus 8 plus X equals minus 2. So this is minus 7. This is minus 7 plus X has to equal a minus 2. So if you move this over here, X is going to equal a minus 5. So in this case, sulfur has a charge of minus 5. Plus 5, excuse me. I got my sign wrong. Plus 5. So you see, if you plus 5 minus 7, you end up with a minus 2. So sulfur in this time has to be a minus plus 5. Now we have the same situation here. Now this is a compound, so this sum is going to be 0. But it's, again, the combination of hydrogen, sulfur, and oxygen. So again, hydrogen combined with nonmetals is plus 1. There's 2 of them now. So we're going to do 2 of those. Sulfur is what we want to know, and there's 1 of those. And oxygen, again, there's 3 of them this time, and it's minus 2. And all of this has to add up to 0. So this is 2 minus 6 plus X equals 0. So now in this case, if you do the algebra here, you get plus 4. So here it's plus 4, and here it's plus 5. Let's do this one. We have potassium, chromium, and oxygen. Okay, potassium is one of those 1A left-sided elements, so it's 2 times plus 1. Plus 1 is its common oxidation state. Again, oxygen is minus 2, so 4 times a minus 2. And then we have, in the middle here, we have X. We don't know what chromium is. And all of this has to equal 0. So we have 2 minus 8 plus X equals 0. So X this time has to equal plus 6. The last one, we have sodium, carbon, hydrogen, and oxygen. And all of that has to equal 0. Sodium is in the 1A group, so it's plus 1 plus 2 times X plus, this is again bound with a nonmetal, so it's plus 1, 3 times plus 1 plus 2 times a minus 2. So we have plus 1 plus 3 plus a minus 4 plus 2x equals 0. Well, this is 0, so 2x equals 0, and x has to equal 0. So in this case, carbon is 0, and that's perfectly reasonable, and it's allowed. Okay. So here's something like this will be on the final. So let's move on and look at naming. With that oxidation situation, let's look at naming. We talked about this once, but I want to go over it again. First of all, how do you name binary compounds? You name binary compounds by giving the name of the cation, calcium, hydrogen, etc., and then the anion takes the suffix IDE. So, first of all, a binary compound is a compound with two elements. They are always, or almost always, ionic compounds. The first name is the name of the cation, and the second name is the name of the anion with IDE suffix. So, for example, the cation here is sodium. The anion is fluorine, so it's sodium fluoride. Now, when I say it has two elements, it can have more than two atoms. It's just two elements. So this one, the cation is calcium, the anion is oxygen, so it's calcium oxide. Now, in situations where you have a binary element that has a metal that can have more than one oxidation number, and it's combined with a nonmetal, remember that's where we use the Roman numerals to name. So, for example, iron combined with chlorine can either have an oxidation state of +2 or +3. If it's +2, it's iron 2 chloride. If it's +3, it's iron 3 chloride. Now, the other type of binary compounds are covalent binary compounds. All the ones in that last slide, all the ones that we just went over, were ionic compounds in which you were combining a metal with a nonmetal. Now you can also have binary compounds that are covalent, which would mean that they're both nonmetals. Again, the first and last name are named the same way. That is, the cation is named and the anion is named with an IDE suffix. However, if more than one compound is possible with these two elements, then you use the Latin prefix to differentiate the various possibilities. So, for example, you have carbon and oxygen. Both of these are nonmetals. Carbon and oxygen can combine as on the left with two oxygens or on the right with one oxygen. So you use the prefix. Actually, I think someone corrected me that these are actually Greek prefixes and not Latin prefixes. But you use the prefix dioxide to show that it's CO2 and monoxide to show that it's CO. And here are the common Greek prefixes that are used, and I recommended and suggested that you memorize these. And I suggest that again if you have forgotten to do that. Now, the third possibility are the polyatomic compounds, and remember I said that polyatomic means they have more than two atoms involved. A polyatomic ion, this was on your quiz, a polyatomic ion is a group of elements that travel together that act as a single ionic substance. Again, when you name polyatomic compounds, the first name is the same. The second name is the name of the polyatomic ion. And as I told you in class last week, and I'll remind you today, the exception to that is the ammonium ion, which is a cation and not an anion. So this has the carbonate polyatomic ion, CO3. It has a -2 charge. It's combined with potassium here, so the name is not dipotassium, but it's just potassium carbonate. It's not dipotassium carbon trioxide. It's potassium carbonate. Here sodium is combined with the nitrate polyatomic ion, which has a -1 charge, and this is sodium nitrate. Barium is combined with the sulfate polyatomic ion. Barium is a +2 and the sulfate polyatomic ion is -2, so this is barium sulfate. So let's do this practice. Give the name or the formula for each. By the way, when you read the quiz, make sure you read the whole quiz. Several people missed because they did not read the entire question and failed to give the name when I asked them to write a formula and give the name. So rubidium bromide, rubidium is Rb, and if you look it up on the periodic table, rubidium is a group 1A element, and bromine is a group 7. Rubidium is +1 and a metal, so it's +1, and bromine combined with a metal is -1. The least common multiple here is 1, and so it's RBBr. So let me show you that on here. Rubidium is +1 and Br is -1, and the least common multiple is 1. And so 1 goes into 1 one time, and you don't have to write the 1. 1 goes into 1 one time, and so the formula for rubidium bromide is RBBr. Now this next one, barium NO2, if you look at in your table, you'll see that this is the nitrite polyatomic ion. So you say the cation, which is barium, nitrite, name of the polyatomic, so that's the name for this one. The third one is sodium phosphate. Again, you look into your polyatomic ions, which you're supposed to be memorizing, and you'll see that this one's -3. This is in the group 1, so it's +1. Least common multiple is 3. 1 goes into 3 times. 3 goes into 3 one time. So there's your formula for sodium phosphate. The next one is Al2SO3. Again, you look on your table, and this is the sulfite polyatomic ion. This is aluminum. So it's aluminum sulfite. Now notice none of these have any Latin or Greek prefixes, right? So we don't have to worry about that because we don't have anything where it's 2 nonmetals, and we don't have a situation where there could be more than one possibility. So it's not 2 nonmetals. All of these are metals combined with either a polyatomic ion or with a nonmetal. The last one here is magnesium, which is the symbol Mg, and nitride, IDE, tells you it's just the N. And this is in the 5 group, so it's -3 when combined with a metal. This is +2. Least common multiple is 6. 2 goes into 6 3 times. 3 goes into 6 2 times. Mg3 N2.